Hello everyone. I just welcome you all to the series of alcohols, phenols and ethers. In this lecture series, we will be discussing about ethers. Okay. In the previous three lectures, we have discussed about alcohols and phenols, their physical properties, chemical properties, their preparation we have discussed. And in this lecture, dedicatedly, we will be discussing about ethers. So, what ethers are? If in alcohols the hydrogen is replaced by another alkyl group that give rise to ether. Ether can be either symmetrical or it can be unsymmetrical. If the both R group attached to a compound are same, then it's a symmetrical ether, and if they are different, it's unsymmetrical ether. Okay, so it's like a dimethyl ether. It's diethyl ether. So their common name. It's ethyl methyl ether, and it's ethyl propyl ether. Okay. Next to this is like if it's tert butoxymethyl ether. Okay, give IUPAC name for a compound which is tert butoxymethyl ether. Say there a question like this. So what will be its name? CH3 CH3. Let's draw its structure first. So it will be like this. So its name will be 2-methoxy 2-methyl propane. So that's how their common names and IUPAC names are written. Ethers also show one of the kind of isomerism, that's metamerism. Metamerism is shown by bivalent functional groups. Okay, when the length of carbon chain is different across a bivalent functional group, that's metamerism. When the length of carbon chain is different across a bivalent functional group. Okay, so when the length of carbon chain is different across a bivalent functional group, that is metamerism. For example, CH3O C3H7 or C2H5 all twice O. These both are metamers of each other. Okay, so that's about metamerism. So it's the one of the kind of isomerism which is shown by ethers, esters, and other bivalent functional groups. Next to this is, let's come to the method of preparation of phenols. Sorry, let us come to the method of preparation of ethers. This sound is disturbing. Just give me a minute. Okay, so what's it? It's just methyl. So let's just begin with preparation. So we were discussing about methods of preparation. Sorry, sir. There are too many disturbances in our day-to-day life. Just have to stay focused. Okay, so the first thing is intermolecular dehydration. What is intermolecular dehydration? So it's between same kind of two different molecules. That's something known as intermolecular dehydration. So when the alcohol is reacted with concentrated H2SO4 at 140 degrees Celsius, then what is formed is ether. But what is formed here is the symmetrical ether. But what is formed here is the symmetrical ether. Okay. For preparing unsymmetrical ethers, we need a specific method, that is Williamson ether synthesis. Even if we will use dry Ag2O here, that also can prepare symmetrical ethers. Let's come to Williamson ether synthesis first. That's R, O negative, Na positive plus R dash X give rise to ROR dash. So it is used to prepare unsymmetrical ethers. And the R group here can be primary, secondary, or tertiary. Okay, it can be aryl also, but it must always be primary and must not have any sort of partial double bond character. It cannot be secondary or tertiary, and it also cannot be vinyl or aryl because they have partial double bond character, which will not allow this bond to break and reaction to occur. And in case of secondary and tertiary, there is a elimination and alkene is formed. In presence of such a bulky base, Ro negative Na positive, elimination reaction take place and alkene is formed. Hence, the reaction is preferred only for primary halides. So that's about Williamson ether synthesis. Next is physical properties. So because of R repulsion, they have a large bond angle. First of all, like if you will talk about their state, if we'll start with their boiling points. First of all, how is structure of ether is R O R dash. This is how an ether look like. So this is a polar bond. So this also have a dipole moment also, but this is have certainly lesser dipole moment because of a large bond angle. Bond angle is large. Hence they have low dipole moment. Hence they show just because of this only they show low boiling points. Low solubility in water. And also solubility is inversely proportional to size of alkyl group. Because it causes hindrance. Okay, next is the chemical properties of ethers. If I will talk about chemical properties of ether, first is the reaction with HX. If I will talk about order of reactivity, then the maximum reactive is the, if it's suppose symmetrical ether, then what is formed there is ROH plus RI. Uh, if I will talk about reactivity order, then HI will be most reactive, then HBr, then HCl, then HF. One more thing is the mechanism. So step 1 is the protonation of ether. That is CH3 O CH2 CH3 is reacted with HI and it forms CH3O H positive CH2 CH3. So thus formed here is the oxonium ion. Then there is the attack of I negative over this oxonium ion which yields CH3 I plus CH3 CH2OH. Step 2 is just attack of I negative. Okay, this reaction can be studied in two steps. So first is the formation of oxonium ion. So whenever this question comes now, we have to do this by mechanism only. See, the first thing we will do is we will form an oxonium ion, and if the alkyl groups here are primary and secondary, the reaction will proceed by SN1 mechanism. And if the alkyl group here present are benzyl, allyl, or tertiary carbocation, okay, then the reaction will proceed by SN1 mechanism. For example, if I will take a few examples, it will be easier to understand. Okay, now I have to react this with HI. What I will do, I will form an oxonium ion. Now I negative will attack over it. So if I negative will attack over here, then we have to break this bond. And this bond is having something partial double bond character. So it's difficult to break this bond. So definitely we will go by here and we will take out CH3OI, CH3I. Okay, so and along with phenol, this is formed. Suppose if it's CH2 double bond CH O CH2 CH3. Again, same reaction with HI. We will form an oxonium ion like CH2 double bond CH OH positive CH2 CH3, and then there is attack of I negative, and it can attack either here and it can attack either here. There is a partial double bond character here, so this bond is difficult to break, so we will not choose this path. We will choose the easier path, then that CH2 double bond CHOH plus CH3 CH2I. Next to this is like CH2 double bond CH CH2O CH3. So if I will proceed this reaction, so what is the mechanism here for this reaction? If I will proceed, if I will react it with HI, CH2 double bond CH, CH2, then OH positive Ar CH3. Okay, now I negative have to attack. Where would I negative will attack? Okay, if you will consider SN1 mechanism, then I negative must attack here. Okay, because of this stable carbocation. And if you will consider SN2 mechanism, then I negative must attack on CH3 because of the less hindrance. So definitely I negative will attack on CH2 group because of the stable carbocation being formed. We will prefer that. So CH2 double bond CH, CH2I will be formed here along with methanol. Okay, let us take one more example like CH3 CH2 CH2O CH3. If this is the ether, then what are the products formed and by what mechanism the reaction will proceed? The reaction will proceed definitely by SN2 mechanism, and the products formed will be CH3I plus CH3 CH2 CH2OH. I hope you are getting the difference. Okay, so if, we have seen the hindrance here. If I will explain to you this by mechanism, CH3 CH2 CH2 OCH3 H here, and this is positive. Now I negative will attack. Where would I negative will attack? Here or here? Okay. So if it's proceed, we have to decide either it's proceeding by SN1 or SN2. I have said you, if it's primary, secondary, then definitely it will proceed by SN2. So definitely if it will proceed by SN2, we will see steric hindered. So this position is sterically hindered. So definitely I negative will not go there. I negative will come on CH3. So it's a CH3I plus this alcohol will form there. Okay. So this is how we will see the reaction with HI. This is one of the kind of important reaction. Next to this, for example, tert butoxy methyl ether, if it's okay, then it will proceed by SN1 and the product forms are CH3C, CH3, CH3I plus CH3OH. I hope you are getting it. See, CH3C, CH3, CH3OH, CH3 positive. This is the oxonium ion formed here. Now I negative can attack either there or here. Now if this bond breaks, then a stable carbocation is formed. So easily this bond will get broken and I negative will attack there. Okay, not here because the reaction will proceed by SN1. So we have to see the mechanism also. Okay. So before observing the stability of carbocation or the steric hindrance, what will be the deciding factor for the product is the mechanism. So the mechanism for this reaction is not fixed. We have to predict the mechanism. So while predicting the mechanism can be either SN1 or SN2. So the mechanism here will be SN1. So according to SN1 tertiary, this product will be a major product. That's it. Okay, so that's it. Let's have one more question. CH3C, CH3H, OCH3. Suppose if this is the ether, and now this will proceed either by SN1 or SN2. This will definitely proceed by SN2. It's a simple. If the group is secondary or primary, it will proceed by SN2. If the R group is secondary, primary, or methyl, na, it will proceed by SN2. And if it's a tertiary, allylic, or benzylic, then it will proceed by SN1. Otherwise, if a partial double bond character is there on some bond, if it's vinylic or uh, phenylic, then that bond will not get broken and I negative will attack on some other alkyl group. In that there is no doubt. And if it's tertiary, allylic or benzylic, it will proceed by SN1, and if it's secondary or primary, it will proceed by SN2. As simple as that. Next to this is reaction of ethers with some acids. So they will simply form the oxonium salts. For example, reaction with H2SO4, ROR. If reacted with H2SO4, it will form RO, positive R, and SO4 negative. And if it is reacted with HCl, ROR, positive, Cl negative. Next is electrophilic substitution of aryl ethers. They are similar to that of phenols, so we will not discuss much here regarding them. Electrophilic substitution of aryl ethers. Okay, so it's like OCH3 when reacted with Br2 in the presence of CH3COOH, it will form OCH3 and a bromine here. So this is halogenation. Second is Friedel-Crafts reaction. Okay, so the reactions are similar to phenol and ethers in case of anisole also. So same with sulfonation, nitration, everything is similar. Okay, nitration, NO2 will be at ortho and para position, NO2 positive will be the electrophile. Same with the acetylation. Uh, an extra reaction is there that's known as Fry's rearrangement. Let us discuss that. What is Fry's rearrangement? So Fry's rearrangement is basically we are taking an ester and when it is reacted with anhydrous AlCl3 in the presence of a nonpolar solvent like carbon disulfide, what it forms is ortho and para substituted methyl ketones. This is known as Fry's rearrangement. Same happens if in place of CH3 one C6H5 group is there. Same thing happens with that also. Okay, like it's so same kind of rearrangement will occur here. So that was brief about ethers. So that was the required discussion. Okay. So I hope this was something you all have understood. Thanks for watching the video. Have a good day. Bye bye.